Good morning, all. Welcome to another episode of CSEC Physics with me, Marvin Lee. Today we will look at forces and deformation. In today's lesson, we will look at forces. Now, a force can be defined as any action which can change the size, shape, or motion of a body. Which can. Now, the word can is used because forces do act, but these changes aren't always produced. So for CSEC physics, we define force as any action which can change the size, shape, or motion of an object. Force is measured in newtons, named after the great Sir Isaac Newton. And the newton is the unit of force, but it is also equivalent to 1 kilogram meter per second squared. 1 kilogram meter per second squared. Now this is important because the kilogram meter per second squared unit is the unit of force expressed in terms of fundamental units. Moving swiftly along, we come to types of forces. Now, you would find in some textbooks that forces are listed as contact or non-contact, and that is correct for categorizing forces. But the types of forces that we will basically examine, or the main types of forces we will examine in this syllabus, are fourfold: nuclear, electric, gravitational, and magnetic. Now, let's begin with nuclear forces. Nuclear forces are responsible for holding the nucleus of the atom together. They're the forces that exist between the protons and neutrons in the nucleus of an atom, and they keep the atom and basically us and everything else around us together. Electric forces. Electric forces exist between any two charged particles. Now, whether the charged particles have the same charge or opposite charges, these electric forces still do exist. Gravitational forces. Now, gravity tends to get overlooked because we live all our lives with gravity, but gravity is an incredibly strong force. It's the reason that you can't leap tall buildings in a single bound like Superman, and it's also the reason that what goes up must come down. Gravitational forces essentially exist between any two masses. So if you're sitting at a table right now and there's a pencil next to you, gravity is pulling that pencil to you. Yes, your gravity. The reason it doesn't move is because we are in the gravitational field of a much larger object, planet Earth, and that tends to override all other small gravitational forces. Finally, we have magnetic forces. If you've ever looked at any X-Men movie, you would realize that Magneto is incredibly strong because of this. So we tend again to often overlook magnetic forces until we run into one of those freezers that is really tough to open and you have to strain to lift the lid because the magnets that tend to hold it down are incredibly strong. Magnetic forces exist between any two magnetic poles, and just like electric forces, it really doesn't matter if the poles are like or unlike, similar or dissimilar. As long as you have two magnetic poles, you have magnetic forces. Now, effects of forces. Again, for this syllabus, the CSEC syllabus, we only look at two effects of forces: the turning effect, or moment of force, and this is when a force causes an object to rotate about a fixed pivot, and deformation. Deformation is the focus of today's lesson. And in this lesson, we will define deformation, we will give the law that governs it, we will give the types of deformation, and we will work a few problems. So stay tuned. Now, let us look at deformation. Deformation occurs when a force changes the size or shape of an object. I have in my hand a piece of blue Play-Doh. If I apply a force by just simply squeezing it, I have changed its shape. Compared to how it was before, I can say that I have deformed it through the application of a force. Now, deformation does occur more often than we actually do think. In sport, I'm sure if you played cricket often enough, hardball cricket as it's called, you would realize that the ball does get softer with time, and that is through two things: repeated contact with the ground when the bowler delivers the ball, and also repeated contact with the bat when the batsman plays a stroke. Deformation is of two types: plastic or elastic. And to prove my little point, I put down my trusty Play-Doh and I find a friend. A plastic bag. Yes, a plastic bag. If I stretch this plastic bag and I let it go, it is stretched still. It does not change shape. I can keep stretching it and it eventually does tear. This is plastic deformation. Permanent deformation it is called. Elastic deformation is temporary in nature. It occurs, for example, in everyday life with things like socks, leggings. Those are elastic items that stretch and then return to their original shape once they are no longer being stretched. So do remember, elastic is two types: plastic, permanent, or elastic, temporary. Elastic deformation is governed by Hooke's law. Yes, Hooke's law, Hooke', kind of like the villain from Peter Pan. And Hooke's law says force is directly proportional to extension. Force applied is directly proportional to the extension obtained. This is only for elastic objects. Does it apply to elastic objects all the time? No, it does not. It applies to elastic objects up to the elastic limit. Now, the elastic limit is a bit self-explanatory. It is the point at which elastic behavior stops, or the point past which elastic behavior no longer continues. It depends on how you want to define it. So, once again, just to recap quickly, Hooke's law governs the behavior of elastic objects only, not plastic deformation, okay? Doesn't cover it. And it is only applicable up to the elastic limit. Continuing, we have to look at the equation that Hooke's law produces. Hooke's law clearly states that force is proportional to extension up to the elastic limit. But this is an expression and it produces an equation. Now, our equation is really simple. Our equation is F, force measured in newtons, is equal to K, a quantity called our spring constant, times our extension obtained. Now, our extension can be measured in millimeters, centimeters, or meters. It's not incorrect to express it in any one of those quantities. This is our equation. Our equation leads us to be able to, or allows us rather, to be able to plot a graph. Now, that graph has many uses, and it is one of the most common SBAs done at this level. The graph, which is over here, is a plot of force on the Y versus extension on the X. And for any object that can be actually stretched past its elastic limit, it will be a straight line. It will be a straight line up to the elastic limit. At the elastic limit, force is no longer proportional to extension, and the graph begins to curve because it is now no longer a straight line. Let me go that over again. Hooke's law allows us to plot a simple graph, force versus extension. When we plot this graph for any object that we can actually push past the elastic limit, what we will find is that before the elastic limit, our graph is a perfect straight line, starting at the origin. But when we get to the elastic limit, or you will know you have arrived at the elastic limit, when the graph is no longer linear, the graph is no longer a straight line. Once that point is reached or exceeded, you have passed the object's elastic limit. Now, there is one other interesting thing about this graph. One other interesting thing, and that is the gradient of the graph. We will look at that next. This force extension graph has a very unique property: the gradient of the graph before the elastic limit. Now, gradient is usually some change in the quantity on the y-axis divided by a change in the quantity on the x-axis. Let me go that over again. Some change in y, or whatever is on the y-axis, divided by some change in x, or whatever is on the x-axis. So let's plot a, well, not plot a graph. Let's find the gradient of this graph. The method recommended by CSEC is that you establish, or you mark off, a fairly large triangle. Now, this triangle gives you 4 points. It gives you x1 and x2. And along the y-axis, it gives you y1. And if we go up here and come across, forgive me if my line is not perfectly horizontal, y2. Our change in the y-axis is measured from y1 to y2. And our change in x, or the quantity on the x-axis, is measured from x1 to x2. Now, the change is not measured in actual physical length, like 4 cm, 6 cm. It's measured in how much of the quantity do you have here, minus how much ever of the quantity you have here. Okay, so let's make up some numbers just for ease of understanding. Let's assume this is, let's say 8. And let's assume this is 1. Let's assume y2 is 20 newtons. And let's assume y2 is 6 newtons. Just assuming numbers randomly chosen. Again, gradient is change in y divided by change in x. So our change in y is 20 minus 6. And our change in x is 8 minus 1. We get 14 over 7. And this gives us 2. However, our change in length is measured in centimeters, and our change in force is measured in newtons. So this 2 will have units. Looking for some clear space, it would be 2 newtons per centimeter, or it could be written as 2 newtons per centimeter. Sorry, I almost put the negative power there, do forgive me. So, our graph has an important property, it's gradient, and our gradient has units. But wait, whatever do these units mean? If we are to find what these units mean, we have to go back across and look at our equation. We will do so now. We just looked at our graph and we figured that this formula, which we can use to get a graph, gives us an interesting property. The property is gradient, but gradient has a certain significance, not just numerically, but in terms of its application. If force is equal to spring constant times extension, if we are to find the spring constant, we would end up with force upon extension being equal to spring constant. If we looked at our graph, our gradient is what was on the y-axis divided by what was on the x-axis. What was on the y-axis was force, and what was on the x-axis was extension. So force upon extension for a force extension graph gives you the spring constant. Also, for a force extension graph, the gradient gives you the spring constant because the gradient is essentially force or change therein divided by extension or change therein. So the spring constant is essentially the gradient of the graph. Again, let me go it over. Force is equal to spring constant times extension. To find the spring constant, we divide force by extension. But in order to find gradient, we still divided change in force by the corresponding change in extension. It therefore can be concluded that our spring constant is the gradient of a force extension graph. Having examined deformation theoretically, it's time to test a spring. Now, it must be said that it is easier to reach the elastic limit of an object like a spring than it is to reach the elastic limit of a rubber band. For simple reasons, a rubber band is more likely to burst before it gets to its elastic limit, but this spring can actually be stretched to the point where it just becomes a straight wire all over again. It will no longer behave like a spring, and obviously it will not go back to its original shape. So this is our spring. We can see it's taken some amount of stretching, but we will use this today to actually obtain a spring constant for our trusty spring. To stretch our trusty spring, we need force. Now, this force is not generated manually. I'm not going to hold the spring and pull it. I am actually going to use these. Now, this is a kilogram, and it's made up of 10 single 100-gram masses. And what I'm going to do is use this to provide our force. But you're thinking, how can I use this to provide force? If you remember from a previous lesson, we said weight is a product of mass by acceleration due to gravity. We have mass, we have gravity, and therefore we have ourselves some weights. And the weight here will be the force we use to stretch our spring. Next, we have a meter ruler. Now, this is the ruler that has to be used to determine by how much has the spring stretched. This is used to measure the spring's extension. Now, this can be done a few ways. You can actually measure the length of the spring as it changes and record the length each time. Also, you would have to record, excuse me, the original length of the spring. And of course, doing some simple maths, subtracting, taking the old length from the new length should give you your extension. So this rule is just to measure the change in length of our spring. And of course, needed to support all these things, we have a pair of trusty retort stands. Retort, children, not retard. Retort stands. And this represents our apparatus, so it's time for us to put them together and do a simple experiment. The most important thing, before I forget, is we have to put this ruler vertically. Now, this is a bit of a challenge at times for two reasons. One, you need a retort stand with a clamp that can actually hold the ruler vertically. And the other problem is many times the edge of the ruler in and of itself is not straight or square. The edge is a bit worn, so it creates a slightly round surface and you're not sure if it's vertical or not. But what I would recommend is whenever you do mount your ruler, you take a few steps back and you actually examine it from a different perspective just to ensure that it is vertical, because it can't be leaning to the side. You wouldn't actually get an accurate change in length if it is leaning to the side. So ruler first, spring second, and we'll get our experiment done. Now, with our ruler in hand and our trusty retort stand, we try our best to place the ruler between the clamp of the retort stand. Once it is held there, we just tighten the clamp, as this one is definitely a bit on the wobbly side. And then comes the issue of simply ensuring that it is vertical. Now, I have the benefit of having a ruler with a fairly straight edge, so I would assume for the most part that my ruler is vertical. Now, one of the things you also have to be sure of is that you observe the direction in which the numbers are either increasing or decreasing along the ruler. Because if you have the numbers in the wrong order, you might actually be a bit confused with the change in length of the spring. So I have 0 at the top and 100 cm at the bottom, so that as the spring gets stretched, the numbers would increase, or the numbers seen would increase. Just a small point to note. Now, what I have to do next is I have to take my other retort stand, place it in front of the ruler in such a way that when I do close the clamp around the spring is right up against these numbers, so that I'd be easily able to determine, one, its length, and two, its length as it changes, or as I add mass or stretch it. So having attached our meter ruler to the first retort stand, we get our second retort stand and our soon-to-be stretched spring, and again we place the top hook or loop of the spring between the clamps of the retort stand. Now, one of the problems you just might face is that if the retort stand is old enough, it may not necessarily close, but as you can hear, I am actually fighting this retort stand into submission, and poof, yes, here it is. Spring firmly held in clamp of retort stand. Now what I have to do is bring back the retort stand with the ruler, place this retort stand with the spring in front of the ruler, and I will be able to accurately get a measurement of the spring's length. Now, what can be done also is that you can actually measure the length of the spring before you even mount it in the apparatus. That is actually recommended, but you can do this as well, okay? Neither approach, I should say, you shouldn't exactly favor one over the other, but just ensure that you measure the length of the spring before you start stretching it. Now, we have set up our first retort stand with our meter ruler, fastened with some Play-Doh we now have to place our second retard stand with our spring in front of our ruler. Now, before we do anything else, we have to ensure that we determine and record the length of this spring. We do that by just ensuring this spring is a bit, you could say, firmly placed against the ruler, and you record its length. Now, the length begins essentially from the first coil, the start of the first coil, and ends at the end of the last coil. According to this, it begins at 42.4 cm, 42.4 at eye level, yep, and it ends at 61.4. So 42.4 to 61.4, that works out to what? 19 centimeters of length. 19 centimeters of length for our spring. Now, the next step is to use our trusty mass holder, attach it to the base of the spring, and observe the change in length. It ended at 61.4 centimeters. So we know all lengths or changes therein will be with respect to the 61.4 at the bottom. So what do we do here? We have to hook this on gently to the base of our spring. Now, when we do this, we notice that because there is certain width to the mass holder that the spring does not have, we have to move the spring forward ever so slightly. Ever so slightly. We don't want swinging or a whole host of vertical motion. So we now begin to measure the changes or the new lengths as a result of our mass. And again, please try to avoid any vertical movement, because we don't want, we don't want this happening. We could just gently bring the system to rest, or as close to rest as possible, and we do our measurements from that point. 1 second. 64.5 centimeters. 64.5. So we were at 61.4. We now are at 64.5 for our first 100 grams of mass. We have to now add a second mass. And again, we try to act in such a way as to minimize the spring's vertical motion. You don't drop the mass onto the mass holder, you lower it gently and you release it. You will get some motion, it's a spring, it's unavoidable. But again, you don't want to have a large up and down movement. The lower extremity of the spring is, according to my eyesight, it's at 67.7 centimeters. 67.7. So we went from 61.4 to 64.5 to 67.7. And now we just add our final mass. I say final mass because you just need about, at minimum, 3 data points. And also we might be running out of real estate. So adding another mass, and again, ensuring that we do our best to keep it from oscillating up or down. We measure where we now are. And according to this, it's at 71.2. So 71.2, and we were at 67.7. That's an increase of around what? 3.5 centimeters roughly, which is again consistent because we're getting around the 3.2, 3.3, 3.4 mark. Not bad. And we can try one more just for the sake of it. We load a final mass again, being cautious as to not put the system into vertical oscillation. We measure the change in length. And this is 76.4. 7 to 6.4, and this is a much larger increase. We were at 7 to 1.2, I believe, and now we are at 76. So the increase is significantly larger, and this will happen. And what it means is that we probably put a little more mass on the spring than the spring can handle. So here it is, simple experiment. Load the spring, record changes in length, record data. And this would give you your data for the Hooke's Law lab. Now, we use values of mass. It must be noted that these masses have to be converted to weight. Again, using the formula, weight is mass by acceleration due to gravity. And the mass, along with the corresponding extension obtained, would give us the points needed to plot our force extension graph. And this is how you actually obtain a force extension graph for a simple spring. Now, we obtain the graph, or we have the data for the graph. What are we going to do with it? Whenever you obtain this data, you can plot the graph, obviously, and you can also use the graph now to find your spring constant. Because as we did earlier, the gradient of a force extension graph gives you the spring constant. So this information can all be used to calculate the spring constant of this spring that we have here, which raises another point. That spring constant only applies to this spring. Other elastic objects might have the same spring constant numerically, but the value we found here applies to this spring specifically. So there you have it. Force versus extension, Hooke's law and deformation, and a simple lab. Thank you.